These are some examples of writing reaction products from the first part of chapter 19. And this particular exercise is something I often do the day after students come back from spring break, for whatever that's worth. So we'll start with some where we're making, it looks like imines, and then some where we're hydrolyzing acetals and imines and enamines. So the first one, we have a ketone and ammonia, and ammonia acts in the same way that a primary a primary amine would, RNH2. And so the product that we're going to get, sometimes students find that it's helpful to draw out the carbanolamine. Sometimes students don't find it's helpful. And then that's going to go on to the imine by losing this OH and one of these H's. So in order to make an imine, you need to have a nitrogen-based compound that has at least 2 hydrogens on the nitrogen. So in the second one here, we have another ketone and a secondary amine. And so we'll draw the intermediate that we get, the carbanolamine. So there's your carbanolamine. And now, if you look at this, there's no hydrogen on this nitrogen, so it's going to have to remove its hydrogen from a carbon to make an enamine. The way this particular molecule is set up, there's no hydrogen on this side, so it has to pull it from that side. And so our resulting enamine is going to look like that. So enamine, it has an alkene and an amine. And it turns out that this particular secondary amine is kind of a classic one that's used in synthesis that we'll talk about in 2 chapters. All right, this one's kind of interesting because now we have the amine and the carbonyl tied together in the same molecule. The darker green will be better. So if we number from the carbonyl, 1, 2, 3, 4, 5. So when the nitrogen attacks the carbonyl carbon, we're going to end up with a 5-membered ring. A really bad 5-membered ring that looks like that. So we have our primary amine. And now this can lose the elements of water. And if the program will cooperate, we can at least draw a somewhat better looking 5-membered ring. And that's going to give us this final product, this imine. And if we go back and we number here, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. So number 4 looks kind of weird and scary because this orange compound is kind of weird and scary. And it turns out that this molecule, which has the name of 2,4-dinitrophenylhydrazine, which, because organic chemists are naturally lazy, we're going to abbreviate as 2,4-DNP, is a reagent that's commonly used in qualitative analysis for both aldehydes and ketones. So we're just going to treat this like a really big, fancy primary amine. Hopefully I won't run out of room here. Make this a little bit bigger. So we have the nitrogen that does the attacking is this nitrogen. So we'll have that nitrogen, and then it's attached to an NH, which is attached to a benzene ring. And then we have nitro groups that are ortho and para to this hydrazine group. And this compound is referred to as a hydrazone. And they're useful for two reasons in qualitative analysis. One is that they're generally solids, so you observe a precipitate. And the color of the precipitate depends somewhat on the aldehyde or ketone, because if there's more conjugation, there'll be a darker orange to a red, whereas with less conjugation, there'll be a lighter orange or an even lighter orange. The other thing you can do with these in qualitative analysis is you can isolate the solids and make a derivative, and that gives you a second melting point. So you've got that, and that melting point in addition to the boiling or melting point of your original compound. So the next group of these all involve hydrolysis of acetals, enamines, imines, and so on. And so it's helpful to take a look at what happens here when it stops bouncing around. And so in these examples, I've highlighted in green the former carbonyl carbon. So if you compare like the acetal to the carbonyl, the imine to the carbonyl, and the enamine to the carbonyl compound, we'll do that in green also. So there's the carbonyl, there's the carbonyl, there's the carbonyl, and then you can see in the corresponding substitution or addition compound, you've got that carbon. So the carbon that is attached to the carbonyl in the aldehyde or ketone is the one that gets attached to the heteroatom or heteroatoms in the acetal, imine, or enamine. It's easy to get distracted by this double bond. So when you do a hydrolysis, when you add water and generally acid to these, the bond or bonds that you're going to want to break are the bonds to the heteroatoms that are attached to this former carbonyl. So the trick is to find the former carbonyl and then write the products. And one example I didn't do here that's a common acetal and hemiacetal are carbohydrates. So if we look at this first one, the two bonds that we're going to break are those, and theirs are what's going to be our carbonyl. So we're going to make cyclopentanone, and then we have an alcohol, a diol that has two methylenes in it. And again, this particular acetal for this alcohol is commonly used as a protecting group. So here we have an imine with a carbon-nitrogen bond. And so again, we're going to break the bond to the heteroatom. And sometimes it's easier just to draw it kind of in the same orientation. And then we have N. And we're going to add two hydrogens to that to complete the octet. And also we know because this is an imine, which by the way are sometimes called Schiff bases, that we need to end up with a primary amine. So here, a lot of times students get distracted by this piece. They figure that's the important piece, so therefore that must be the carbonyl compound. But the trick is to stay focused and realize that here is the carbon that's attached to two oxygens. So that is the carbon that's going to get attached. This is the carbon that is going to become the carbonyl. So we end up with that, which always looks strange to me. So I'll go ahead and put the two hydrogens in. And there are the two hydrogens again. And then our other piece is going to look like that. One thing I forgot with number 6 is that in acid, that generally these amines are actually going to be protonated. So at the pHs that these hydrolyses are done, it's going to be acidic enough that you end up with this as your final product. And that actually helps to drive the reaction to completion, which I talked about when I went over the mechanisms. And that's why going down here, I wrote both the structures of the amines and the corresponding protonated versions. All right, so this one, we need a new color. I guess blue is going to have to do. So again, we need to find the carbonyl carbon, which is the one attached to the heteroatom. So the bond that we're going to break is going to be that bond. So we're going to end up with that as our ketone. This time I'm going to remember to draw it as it would appear in acid. And then that's going to be your protonated amine. And again, that makes sense because we started with an enamine and now we have a secondary amine. And in terms of writing products on tests, you'll probably get full credit whether you write it protonated or not, but you should understand that it's protonated and why that's helpful to the overall reaction. All right, this thing. So again, half the problem is finding the carbon that becomes the carbonyl. So we're going to look, since this is an acetal, we're going to look for the carbon that is attached to two oxygens, which is this one. So the bonds that we're going to break are these two. And so the circled carbon becomes the carbonyl. And I'm just going to take this thing and flip it up like that. So we have the bridgehead, and then we have the carbon with the carbonyl. And yeah, there's a more elegant way to write that, but I'm not going to do it. All right, so the last one that we have is this one. And I have a note here that this is actually, it's a steroid. That's used as a drug, and actually this is a prodrug, meaning that it hydrolyzes or converts to the actual drug. So again, over half the battle here is figuring out which carbon is the carbonyl, and if you look in this whole big complicated structure, the only carbon that's attached to two oxygens is this one. So when we go to draw the product, I'm not going to draw both of them. So there's your carbonyl. And so your carbonyl product is acetone. And I'm going to leave the drawing of the other product as an exercise for the student, as they say. And notice in the name of this compound, it's called an acetonide, and that indicates that it is an acetal of acetone. And again, this is used. And here is the promised example involving a carbohydrate, which I wrote out while I was recording it before, but I've had various cat and screen issues. So I'm just going to point to things since I now have it written out. So here we have the structure of D-glucose, and it is a hemiacetal. It has an OH here, and an OR, which makes it a hemiacetal. Here's the carbon that will hydrolyze to a carbonyl that's attached to two oxygens. And again, we know that this is a hemiacetal because one of those oxygens is associated with an OH group. So the bond that we're going to break when we hydrolyze this is going to be the one to the OR. Right, so there's the bond you're going to break. And so when we do this hydrolysis, this is the OH turns into the carbonyl, and then I just got lazy and I drew it kind of the same conformation as I did on the ring. And this is the so-called open chain form that's in solution less than 1% of what glucose actually looks like. You can also take the glucose, this hemiacetal glucose, in the opposite direction and under relatively mild conditions react it with an alcohol and acid, and that's going to convert only the hemiacetal OH to the full acetal. These other OH groups